Hello everyone and welcome back to a video on calculus. In this video we are going to introduce the idea of the derivative. So everything's really built around the idea of the difference quotient. So let's talk about what the difference quotient is, and then we can talk about the idea of a derivative. So let's say we have this function. I'll call it f of x. And then we're starting at this point, x. We know that for this x value, we can find a y value. So this would be the y value f of x. And then we're going to scoot over a little bit to the right. It doesn't matter if I go to the right or to the left. I'm just going to go to the right to be generic here. So this new x value is x plus h because I moved over h units. And then if I go up to the graph, I can find the y value, which is x plus h. So I've got these two ordered pairs, x, f of x, and then x plus h, f of x plus h. And then since I have two ordered pairs, I can find the slope. So the slope is going to be y2 minus y1. So I'm subtracting those y values over x2 minus x1. I'm going to simplify that. So this is giving me the slope of the line between these 2 points here. And this is called a secant line. So this is the slope of the secant line. In calculus, we are thinking about what happens as the distance between these two x values gets smaller and smaller and smaller. And you can see that as that distance gets smaller, maybe this is my new h. So then my new line would look like this. And then if we get even smaller, so now maybe that h is right here. You can see how it's changing that slope of that line, and we are approaching what's called the tangent line. So if we want that distance to get smaller and smaller, we could think about taking the limit as h goes to 0 of that distance, or of that slope. And that's what would give me the slope of the tangent line. This is also called the derivative, and we're going to talk about derivative notation here in just a few minutes, f prime of x. So then if we want to know the slope of the tangent line at any particular x value, we could find that derivative and we could plug in the x value. Or we could think about taking that limit as h approaches 0 and plug in that value in here. So we've got two ways to think about it. I prefer thinking about it this way and then plugging in the x value, and that's the way I'm going to work through this video. So let's look at a few examples. So we're going to find the derivative, and let's talk about derivative notation. You're going to see this prime notation that's read f prime of x, or you can see it written as dy over dx. Both of those mean you have the derivative. So if I want to find that here, I'm going to take the limit as h approaches 0. It's going to be f of x plus h minus f of x over h. So we're going to plug in x plus h for the x's. And then we're going to subtract the original function. And then we're going to divide by h. So we're going to take the limit, excuse me, as h goes to 0. We're going to square this out. So that's x squared plus 2xh plus h squared plus x plus h. And we're going to distribute the negative all over h. You can see some things cancel. So I'm going to take the limit as h goes to 0, 2xh plus h squared plus h over h. And we could factor out an h in the top. And then we can cancel those. So I'm going to take the limit as h goes to 0. Let me see if I can move this over a little bit. 2x plus h plus 1. And if I plug in 0 for h, I'm going to get 2x plus 1. So we would say that is the derivative of this function. And then once we have the derivative, then we can find the value of the slope of the tangent line. So we're going to plug 1 in for that. So we're going to have 2 times 1 plus 1 is going to give me a 3. So the slope of the tangent line is 3. Let's do another one. Let's look at number 26. So we want to find the derivative. So that's the limit as h goes to 0, f of x plus h minus f of x all over h. So the limit as h goes to 0. So we're going to plug in x plus h. Subtract the original function all over h. So notice if we were to plug the 0 in here for h, I would get 0 over 0. Same thing would have happened up here. If I would have plugged in, I would have had 0 over 0. Remember, that's a key to let you know you need to do something else. The last one we factored, this one we're going to use our multiply by the conjugate trick. What you do to the top of the fraction, you've got to do to the bottom. And then we're going to FOIL. So there's a parentheses here and there's a parentheses here. So fronts will give us x plus h minus 2. Notice the outsides and the insides cancel. And then the last, when I multiply by this, I'm going to have the negative, and that square root and that square root, when I multiply them together, is going to give me just the x minus 2 there, over h times square root x plus h minus 2 plus square root x plus h. Okay, notice I did not distribute. I need to see if I can cancel this guy. It's causing me a problem. So if we were to subtract x minus x, those are going to cancel. Negative 2 minus negative 2, those are going to cancel. So we are left with the limit as h goes to 0 of h over h square root x plus h minus 2 plus square root x plus h. As you get, now those cancel. If I look at what happens as h goes to 0, I would plug a 0 in here, so this is just going to be x minus. I just realized I wrote this incorrectly. Back up here, I've got square root of x plus h minus 2 plus square root of x minus 2. This should be a minus 2 down here instead of the h. So let me go back and correct this, and you can see how this is going to simplify in just a minute. This would be a minus 2 here. This would be a minus 2 here. So this is the square root of x minus 2 here. And now you see I have two of those. So my derivative, f prime of x, is 1 over 2 square root of x minus 2. And they're asking us about the value of 6. So 6 minus 2 under that square root. And that's going to be the square root of 4, which is 2. So this is going to be a 1/4 for that value. Let's do one more. We want to look at 1 over x minus 3. We're going to find that derivative, and then we're going to plug in the negative 1. So we're going to take the limit as h goes to 0. This is f of x plus h minus f of x all over h. So I'm going to plug x plus h in for x. And then now we're going to have to simplify this complex fraction. And we've got a couple of ways to do that. Here's what I'm going to do. I'm going to multiply the top and bottom of the big fraction by that common denominator, x plus h minus 3 times x minus 3. What I do to the top of the big fraction, I've got to do to the bottom. Because math is always fair. So I have the limit as h goes to 0. So when I multiply that by this, these are going to cancel, and that's going to leave me with an x minus 3 minus, and when I multiply this by that second fraction, those x minus 3's cancel, leaving me with the x plus h minus 3. Distribute that negative. And again, I am not going to multiply this out. The goal is to try to cancel that h in the bottom. So these are going to cancel, and these are going to cancel, leaving us with a negative h here. Oops, let me write my complete sentence. So the limit as h goes to 0, negative h over h times x plus h minus 3 times x minus 3. And now we can see those are going to cancel. And then if we plug in 0 for h, we're going to get negative 1 over x minus 3 times x minus 3, which is negative 1 over x minus 3 quantity squared. So there's my derivative for this function here. We want to know the value of the derivative at negative 1. So we're just going to plug in a negative 1. Negative 1 over negative 4 squared, which is a positive 16. So we have negative 1 over 16 for the value of that derivative. So let's talk about the notation of the derivative. So we're going to see f prime of x and dy over dx. They both mean the same thing. If the function was a g of x function, like g of x equals x squared plus 2, then the derivative would use g prime. And we would get the same thing that we did. I believe that was actually x. We would get the same thing we did before. Okay, so this means I have the derivative. This is the derivative. We could also see it written as y prime. This notation means I need to take the derivative of whatever follows. So you will see a function in here. I'll call it f of x. Or a shorthand notation would be this with the slash here, which is called the prime symbol. These mean I need to take the derivative. So what does the derivative tell us? It tells us a few things. One thing is an instantaneous rate of change. The derivative can tell us how that function is changing at a specific moment in time. It also tells us the slope of the tangent line. And then the third thing has to do with physics. So if we have an equation that's modeling position at some point in time, then the derivative of the position equation is going to be the velocity equation, and that will tell us an instantaneous rate of velocity. And it turns out also that the derivative of velocity is acceleration.